Hello, geometry students, and welcome back to another probability video. You know what to do. Pause the video, try these problems in your notes, and then unpause them to do them with me. We want to find the number of possible outcomes in the sample space, then list the possible outcomes. So remember, the sample space is all possible outcomes. So we're going to list out every single thing that could possibly happen when we do the probability experiments listed down here. So the first one is you flip 2 coins. Okay, well, if I flip the first coin, I could get heads or I could get tails. Now when I flip the second coin, I could get heads, I could get tails, I could get heads, or I could get tails. So each one of these 4 things is a different possible outcome. I could get heads and then heads, I could get heads and then tails, I could get tails and then heads, or I could get tails twice. So each of these are in my sample space. And this is everything in my sample space. Now, so this would be my final answer. Now, the second question asks, you flip 2 coins and roll a 6-sided die. So we already know, if I flip 2 coins, we already know that this is the possible outcome. I could get heads twice, heads, tails, tails, heads, or tails twice. So if I roll a 6-sided die, I'm going to have each one of these possible outcomes, and then 1, 2, 3, 4, 5, or 6. So basically, I could flip heads twice, and then roll a 1, heads twice, and then roll a 2, heads twice, then roll a 3, heads twice, then roll a 4, heads twice, then roll a 5, and heads twice, then roll a 6. I can do the same thing with heads and then tails. I could flip heads, then flip tails, and then roll a 1. I could flip heads and then tails, then roll a 2. And so on and so forth. I could flip tails and then heads, roll a 1, tails and then heads, roll a 2, and so on. Or I could flip tails twice, and then a 1, tails twice, and then a 2, and then so on. And I'm going to cut to me completing this table, and we'll talk about it some more. Boop. Okay, there we go. I have completed all of the and so ons. Notice that we have each one of our flip 2 coins sample space, and then we've added 1, 2, 3, 4, 5, and 6, because those are all of the possible outcomes. So altogether, there is 4 times 6. There are 24 things in our sample space, 24 outcomes in our sample space for flipping 2 coins and rolling a 6-sided die. Okay, that was a fun review from last lesson. Let's jump into what we have for today. Today is the first part of 2 parts on 12.2. So the second section of chapter 12. And this is all about independent and dependent events. So our learning target is that you know what independent and dependent events are. You need to know what they are. Our success criteria is, can you determine if events are dependent or if they're independent? And you can find probabilities of independent and dependent events. So by the end of this lesson, you need to be able to determine if events are dependent or independent, and you need to be able to find probabilities of both independent and dependent events. So first, some vocab, some important information. Independent events. 2 events are independent when the occurrence of one event does not affect the occurrence of the other event. It's like the probability that you win the lottery and the probability that you trip up the stairs, right? Those independents are completely separate. Tripping up the stairs is not going to affect whether or not you win the lottery, and vice versa. So independent events are when one event does not affect the occurrence of the other event. Now that's what an independent event is, but what is an independent event mathematically? So mathematically, two events, A and B, so winning the lottery, tripping up the stairs, something like that. Two events, A and B, are independent events if and only if the probability that both events occur is the product of the probabilities of the events. So what it means is, if the probability of A and B happening, of winning the lottery and tripping up the stairs, if that probability is equal to the probability of winning the lottery times the probability of tripping up the stairs. So the probability of both of them happening is equal to the probability of one times the probability of the other. Now, if that doesn't make sense, don't worry. We're going to see an example of it right now. So, example 1, determining whether events are independent. So, you'll recognize this question. A student taking a quiz randomly guesses the answers to 4 true or false questions. So, question 1, 2, 3, and 4. We have 4 questions on this quiz. And use a sample space to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. Now, what I want to do, pause the video, think about this. Are these independent events? Do you think that these are independent events? Now, we're going to check, of course, but do you think if I guess question 1 and then I guess question 2, does my guess on question 2 depend on my guess to question number 1? Does question 2 depend on question 1? Pause the video and think about that, and then unpause it, and let's talk. So, your guess on question 1. You could guess true or you could guess false. Your guess on question number 2, you're either going to guess true or false. Does it matter what you guessed, whether you guessed true or false on question number 1? Does it matter when you guess on question number 2? No, it doesn't matter. Unless you're doing some sort of pattern where you go true, false, which don't do those types of patterns. If you're guessing in a pattern like that, maybe it would. But really, what you guess on question number 1 is completely different than question number 2. So we think that these should be independent. That is our guess. Our guess is that yes, they are independent. But we're going to check. We're going to check right now. Because, what does it mean to be independent? Remember, to be independent, it means that the probability of A and B is equal to the probability of A times the probability of B. Now, what is A and B? When we say A and B, A, B, what are we talking about? So, A and B, this is the probability of guessing question 1 correct and question 2 correct. The probability of A is question 1 correct, and the probability of B is guessing question 2 correctly. So, probability of A is question 1 correct, and probability of B is question 2 correct. Now, in order to figure out what is the probability of getting question 1 and question 2 correctly, well, in order to determine that, we are going to need to use a sample space. And this sample space will actually be the exact same sample space that we made in the last video. So, when talking about the 4-question quiz, I could get 0 answers correct. I could get 1 answer correct. I could get 2 answers correct. I could get 3 answers correct, or I could get all 4 answers correct. So remember, I could get, and we'll use I for incorrect and C for correct, just like they did last time. So I could get all of them incorrect. It could happen. I could get 1 correct. That could be the first question, the second question, the third question, or the 4th question. I'm gonna need some more space. I could guess 2 questions correctly. I could get the first and the second question correct. I could get the first and the third question correct. I could get the first and the 4th section correct. I could get the second and third questions correct. I could get the second and 4th questions correct. I could get the third and the 4th question correct. I think that is all. Yeah, because if I get the 4th, yeah, okay. Wonderful. Other options. I could get the 3 questions correct, and that meant that I would get the first one wrong, the second one wrong, the third one wrong, whoops, or the 4th one wrong. And I could get all 4 questions correct, which would mean that I have 4 C's here. Okay, so what is the probability of getting question 1 and 2 correct? Well, let me look through our sample space here. I want question 1 correct and question 2 correct. I want both of these. So, here. Right here, I have question 1 and question 2 correct. And here, I have question 1 and question 2 correct. Here, I have question 1 and question 2 correct. And here, I have question 1 and question 2 correct. See how in each of these red highlights I've done, the first 2 problems have C's in them. We have CC. So that means that the first 2 questions are correct. So 4 out of, how many total do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is 4 out of 16. Now, the probability of guessing question 1 correct. Well, now I'm going to go through my sample space and highlight every single possible outcome that has a C in the first slot. So see how this one has a C for the first question. So I'm going to highlight that one blue. This one has a C first. 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 This one, and this one. All of these have a C in the first question. So, how many of them were there? There were 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 of those, which means that the probability of this is 8 out of 16. Awesome. And the probability of getting question 2 correct. Probability of getting question 2 correct. So now I'm going to go through, and wherever there is the second, wherever the second letter is a C, I'm going to highlight that. So here question 2 is correct, here question 2 is correct, here question 2 is correct, here, 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 and here. And that is 1, 2, 3, 4, 5, 6, 7, 8. 8 purple. So that means that I have 8 out of 16 possible outcomes where question 2 is correct. So now, let me reduce these fractions. If I divide by 2 on the top and bottom, or no, actually I divide by 4 on the top and bottom, I get 1/4. And here, 8/16 is 1/2, so both of these are equal to 1/2. So, is the probability of A and B 1/4, is that equal to the probability of A times the probability of B? So, probability of A times the probability of B. So, 1/2 times 1/2. Is 1/4 equal to 1/2 times 1/2? Well, if I multiply 1 times 1 is 1, and 2 times 2 is 4. So yes, 1/4 is indeed equal to 1/2 times 1/2, which means that the probability of A and B is equal to the probability of A times B, which means, because this is true, because these two things are equal, it means that we are independent. So because the probability of A and B is equal to the probability of A times the probability of B, these events are independent. Yay. And that's our final answer. It asked us, use a sample space to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. And we said, yes, these events are independent. So we are done. We are done, and we can check our answer. So they did the same thing. What is the probability of guessing correct on question 1? 18 out of 16, or 1/2. The probability of guessing correct on question 2 is 18 out of 16, or 1/2. And the probability of guessing correct on question 1 and question 2 is 4/16, or 1/4. And because 1/2 times 1/2 is 1/4, the events are independent. Great, that's just what we did. Perfect. Let's move on. Example 3, finding the probability of independent events. So, we are still talking about independent events, and now let's think about why would this be independent. So it says, as part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on your first spin and a number greater than 3 on your second spin. Now, are these events independent? Is spinning a 5 on your first spin, is that independent from spinning a number greater than 3 on your second spin? Yeah, each time you spin that spinner, it's completely independent of the first time you spin the spinner, you could get anything. Second time you spin the spinner, you could get anything. Event number 1, the first time you spin the spinner, does not affect the second time you spin the spinner. So yes, we believe these events should be independent. Okay, great. So if that is the case, that means that the probability of A and B should be equal to the probability of A times the probability of B, because this is what it means to be independent. If two events are independent, this is true. So, what we can do is we can say the probability of A and B is getting a 5 on your first spin and a number greater than 3 on your second spin. So let's find out. The probability of A is the probability of a 5 on your first spin. So what is the probability of getting a 5? Well, let's see. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 possible outcomes. We could get a 1, 2, 3, 4, 5, 6, 7, or an 8. So we have 8 possible outcomes. And if we're talking about just spinning a 5, well, that is one of our 8 possible outcomes. So the probability is 1/8. We have a 1/8 chance of spinning a 5. Great. Now the probability of B is the probability of spinning a number greater than 3 on the second spin. Okay, now there are still 8 possibilities. There are still 8 numbers on this spinner, but now if we're talking about numbers greater than 3, how many of our possible outcomes are numbers greater than 3? Well, 4 is bigger than 3, 5 is bigger than 3, 6 is bigger than 3, 7 and 8 are bigger than 3. So that gives me 1, 2, 3, 4, 5 outcomes that are bigger than 3. So the probability of landing on one of these numbers that is bigger than 3 is 5/8. Great. So now, if I want to know the probability that I get a 5 on my first spin and a number greater than 3 on my second spin, well, I can take the probability of A times the probability of B, which is 1/8 times 5/8, which is 5/64. And if we want to know a better estimate, we can put this in a decimal, which is 0.078. So that means that we have approximately a 7.8% probability that you will spin a 5 on your first spin and a number greater than 3 on your second spin. So remember, anytime we talk about independent events, you're going to use this definition right here. Alrighty, great. Let's move on. Well, let's see if we were correct. Probability of A is 1/8. Probability of B is 5/8. Multiply them together, 5/64 or 0.078. Perfect. Okay. Next example. Determining whether events are independent. So we're going back to the first example. The first example where we said, okay, now we want to know if two things are independent or not. So probability of A and B needs to equal the probability of A times the probability of B. Because remember, this is what it means to be independent. Okay, so the problem says a group of 4 students includes 1 boy and 3 girls. Okay, so we have 1 boy, we have girl number 1, girl number 2, and girl number 3. Just making notes. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Okay, so we have one student is the speaker and one student is the recorder. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. Okay, we're going to make our sample space in just a second. We know we need to do that. First, we'll make our sample space. But first, I want to think about this. If a girl becomes the speaker, does that affect the probability of a girl becoming the recorder? Well, if one of the girls is a speaker, that's one fewer girls who can be the recorder. Right now I only have 2 options of who can record. So I think it does depend. I think it depends. Who is the speaker affects whoever the recorder is going to be, because there's only 4 students. So one of them is going to go away when you choose who the speaker is. So I think no. I think no, they're not independent. Let's see if we're right. What are all the possible things in our sample space? So, well, let's see. If I want to list all the possible outcomes, I have a speaker and then a recorder. So let's do this. What if I have the boy go first? What if the boy is the speaker? Well, then we could have boy and girl number 1, boy and girl number 2, or boy and girl number 3. So there are 3 possible outcomes here. And you know what? I should write this over here, not where my face is. Next, what if the boy is second? Well, that means that girl 1 could be first, girl 2 could be first, or girl 3 could be first. So, now what if we have no boy at all? If we have no boy at all, that means that girl 1 could go first. And if that happens, we have girl 2 second or girl 3 second. We could have girl 1 go last. So we can just flip these around. We could have girl 2 go first, which would mean, so here's one option of girl 2 going first, but then we could have girl 2, girl 3. And then we could have the opposite of this. We could have girl 3 go first with girl 2 second. So all of these are options. So now what we're going to do, we want the probability of A and B, girl first and girl second. So let's find the probability of girl first and girl second. So that means we're going to bust out the highlighter again, and we're going to highlight every time a girl is first and second. So that leaves us with 6 possible options. Out of, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 total options. So there's a 1/2 chance that we pick a girl first and a girl second. Now, the probability of A, the probability of event A, which is the probability of picking a girl first. If I pick a girl first, so here a girl is first, here a girl is first, and here a girl is first, and all of these also have a girl first in them. So that's 6 plus 3, that's 9. 9 out of the 12 possible options have a girl picked first. And lastly, let's find the probability of event B, which is the probability of picking a girl second. Another color now. So if I pick a girl second, that means I'm going to highlight everywhere where a girl goes second. So that's these 3. And, you know, that's all of these down here too, because all of these have a girl at the end. So again, this is 6 plus 3 is 9 out of 12 possible options. And I can reduce 9/12. If I divide by 3 on the top and bottom, I get 3/4. So now, let's check. We need to check, does the probability of A and B equal the probability of A times B? So does 1/2, because that's the probability of A and B, does 1/2 equal the probability of A times the probability of B? Well, let's see. 3 times 3 is 9, and 4 times 4 is 16. Is 9/16 equal to 1/2? No. No. Yeah, not 8/16 is equal to 1/2, but my 9/16 isn't. So we were right. No. These events are not independent. These events are not independent. And we're done with the question. They wanted us to determine whether randomly selecting a girl first and a girl second are independent events. And we did that. We said no, they are not independent, so we are done with the problem. We can double check that we're right, though. Girl first is 3/4, girl second is 3/4, girl first and second is 1/2. 3/4 times 3/4, not equal to 1/2. So yay, we were correct. Okay, we have one more example for today. But first, we're going to talk a little bit more about dependent events. Because remember, our learning target and our success criteria said that you know what independent and dependent events are. So, in example 1, it makes sense that the events are independent because the second guess on, remember, these are the true or false questions that we're guessing on. The second guess should not be affected by the first guess on your quiz. In example 2, however, the selection of the second person does depend on the selection of the first person because the same person cannot be selected twice. That is the key for the dependent events. Anytime you have a situation where the same person or the same thing could be picked twice, you don't want to have any overlap. So, if the same person could be picked twice, you're going to have dependent events. So 2 events are dependent events when the occurrence of one event does affect the occurrence of the other event. So if one affects the other, they are dependent. And this conditional probability, we are going to talk more about this in the next lesson. The next lesson is all about conditional probability. We're going to talk a little bit about conditional probability today. And what the conditional probability is it's the probability that event B occurs given that event A has already occurred. That is what conditional probability is. And we write it like this. We write it probability of B given A. So what is the probability that a girl is picked first given, or excuse me, that a girl is picked second given that a girl was already picked first, right? Because it's going to change. The probability that a girl is picked second is going to change based on if you pick a boy first or if you pick one of the other girls first. So that's what conditional probability is, but we're going to talk about it more on the next slide. So the next slide talks about probability of dependent events. And in words, let's read it in words first. If 2 events, A and B, are dependent events, then the probability that both events occur is the product, multiplying, the product of the probability of the first event and the conditional probability of the second event given the first event. So in symbols, it looks like this. Remember that we said the probability of A and B equaling the probability of A times the probability of B. This is for independent. This is for independent events. And the probability of A and B equals the probability of A times the probability of B given A. This is for dependent events. And you see, independent events, you just have A and B, you have them separate. Probability of A, probability of B. When we talk about dependent events, you can see probability of A and then probability of B given A. So the probability of B knowing that event A already happened because they depend on each other. Okay, so now that we've talked about what it means mathematically for events to be dependent, let's move on to our last example for today. Finding the probability of dependent events. So, remember, the probability for dependent events, the probability of A and B is equal to the probability of A times the probability of B given A. And we're going to talk more about this as the example goes on. So, let's read first. A bag contains 20 $1 bills, 20 $1 bills, and 5 $100 bills. Okay. You randomly draw a bill from the bag. So we take some money, we take one bill out of the bag and set it aside. And then we take another bill out of the bag. Find the probability that both events A and B will occur. So we want to find the probability of A and B. And event A, they tell us right here, event A is the first bill is $100. And event B is that the second bill is also $100. Okay, so first, let's find the probability of A. The probability that the first bill is $100. Well, how many total bills are in this bag? I have 20 $1 bills and I have 5 $100 bills. So altogether, I have a total of 25 bills in the bag. Okay. So the probability that the first one is $100. Oh, whoops. I wrote 1,000 over here. My bad. $100. The probability that the first bill is $100. Well, there are 5 $100 bills in the bag. So there's a 5 out of 25 chance that we pick a $100 bill. And we can reduce this. If I divide by 5 on the top and the bottom, I get 1/5. So there is a 1/5 chance that I pull out a $100 bill. And that makes sense because there's only 5 $100 bills and there's 20 $1 bills. So 1/5 of the bills in the bag are $100 bills. Okay, beautiful. Now we found the probability of A, but we need to find the probability of B given A. We need to find the probability that the second bill is $100, knowing that the first bill was a $100 bill. Okay, so let's think about this. If I pulled a $100 bill out of the bag, that means I took one of the $100 bills. So now there's only 4 $100 bills in the bag. Because I took one out. The first bill that I took out was $100 and I put it over here. So the $100 bill is over here. Now I only have 4 $100 bills. Which means that there are only 24 total bills. Before there was 25, but I took one out. I took a bill out of the bag. So now I have 24 total bills, and 4 of them are $100 bills. So basically, we took what we had before, but we subtracted 1 from the top and the bottom, because there is 1 fewer bills in the bag, and there's 1 fewer $100 bills in the bag, because the bill was a $100 bill. And we can reduce this. If I divide by 4 on the top and bottom, I get 1/6. So now if I want to know the probability of A and B, I need to take the probability of A, which was 1/5, times the probability of B given A, which was 1/6. And 1/5 times 1/6 is 1/30, which is approximately 0.033. And if I turn that into a decimal, that is approximately 3.3%. So not a great chance that you'll get 2 $100 bills in a row. Okay, beautiful. That is our last example for today. We can see if we were right. Yeah, 5 out of 25, 4 out of 24, which is 1/5 times 1/6, or 1/30. 4 of the remaining 24 bills are $100 bills. Yeah, beautiful. Okay. Independent events, dependent events. Now is a good time to check your understanding of the learning target and the success criteria. Do you know what independent events are? Do you know what dependent events are? Can you determine if 2 events are independent or dependent? And can you determine the probability of independent and dependent events? Make sure that you can do all of those things. That was the goal of this lesson. If you have any questions about this lesson, please talk to a friend, talk to me, talk to your teacher, rewatch the video, do something to get those questions answered. All of these are problems that you can do to practice the skills you have learned in this video. But of course, remember to be sure to do the homework that your teacher has assigned as well. And as always, let's end our lesson with a launch, shall we? Today's comes from Roald Dahl, and he says, "If you have good thoughts, they will shine out of your face like sunbeams, and you will always look lovely." Now this might sound silly. If you have good thoughts, they'll shine out of your face. Like, it sounds a little bit silly. But it's true. The better thoughts you have, if you have good thoughts, if you have a better attitude about things, I have the power to change my life. I enjoy math class. I enjoy the things that I'm doing. I'm going to work hard. Life is good. If you have a good attitude about things, you're going to be a happier, more upbeat person. And it'll shine out of your face like sunbeams. But if you have a bad attitude about everything, I don't like math, probability's hard, I don't like life, everything sucks. Like, of course, if you have that sort of attitude and you're all grumpy all the time, yeah, no sunbeams are coming out of your face, only clouds out of this face. So, and that's not to say that there's not a time for cloudiness. There's a time to be cloudy, but if you want to look lovely, if you want to have sunbeams dancing out of your face, have good thoughts. Good thoughts, good attitude, sunbeams out of your face. Okay, so that is my launch for you today. Take it with you as you go throughout your day. Have a wonderful rest of your day, and thanks for being here. Thanks for watching. Bye.